This is wave phenomena higher level. Describe the nature of standing or stationary waves. You have to consider energy transfer, amplitude and phase. So a standing wave or stationary wave is basically trapped between two boundaries. The energy is trapped, the wave is not able to go outside of these two boundaries. A progressive wave, however, is free to travel away, and to travel away from beyond any boundaries. And as the wave moves, the amplitude stays more or less the same. In a standing wave, the amplitude changes at different parts of the standing wave. However, with a progressive wave, the amplitude decreases over a long time, because the energy spreads out. With a standing wave, the energy is trapped. We have and also the amplitude of oscillation varies along the standing wave. At different places, sometimes it has a very large amplitude, sometimes it has a very small amplitude. We have points of constant phase difference, and these are called nodes and antinodes. When they cancel out, when the wave we have destructive interference, they're called nodes. When they have constructive interference, that's antinodes. So when there's a phase difference of half wavelength, it's going to be a node. When there's a phase difference of a whole number of wavelengths, it's an antinode. Now this is the best way to do this, is the Fent demo. Which it starts from the left with a disturbance above the axis. So we have a wave. As expected, this appears to be a progressive wave, a travelling wave which is moving from left to right. We have a boundary here where it's fixed. Now we know that when the wave reaches a boundary, it will reflect, and it will reflect on the other side of the equilibrium line, and so you see this, it gets reflected there. The blue gets reflected there, and then on the other side. Now what we see happening is that we don't see the separate blue and red waves anymore. The red is the incident, the blue is a reflected wave. What we see is the sum of the two waves, and we see basically what is called a standing wave. When they're in phase, that's when you get a double amplitude. Here we get another double amplitude here. The node is where they are constantly out of phase by half a wavelength. They are constantly out of phase, so it will always be destructive interference. This oscillates between a maximum, a double maximum, and a double minimum, which will be there. So this is basically what a standing wave is. Okay, so waves are reflected at a boundary. The wave interferes with its reflection, and that's the pattern that you get. When you have constructive interference, you have the antinodes. When we have an integer number of wavelengths path difference. Points of destructive interference is when you get half wavelength path difference. Lambda over 2, 3 lambda over 2, 5 lambda over 2, which is 1 half, 3 halves, 5 halves wavelength. Also remember that the phase changes when it reflects from a fixed point. Okay, and this is a pattern we see. This will oscillate from the double crest to double trough, and vice versa. At the end, and in the middle, and on the side, we have at this end we have a node. This is where we always have destructive interference. They're always in antiphase. Okay, let's go back one. So this is the antinode. This is the antinode. These are the nodes. Okay. Here, the boundary conditions are such that it is tight at each end. This demands that there will be a node at each end. This is basically called the lowest frequency you get. The longest wavelength is called the fundamental, or the first harmonic. This is no longer the fundamental. This satisfied the boundary conditions because we have a node here and a node here, but we actually have a higher frequency because we have a shorter wavelength here. And here again, the boundary conditions are satisfied. It's a node here, a node here. But we can get any number of nodes in here, and therefore we get different harmonics. With an open pipe, for example, open at each end, this demands that there is an antinode at each end. This is equivalent to 1/2 of a wavelength. Here again, this is an open pipe, open at each end. This demands that this is an antinode, that's an antinode. But this is allowed, but we get a high frequency because this is one complete wavelength, and so on. This is another condition. This is a pipe which is open at one end and closed at the other end. Where it's closed, this demands that it's a node. Where it's open, this demands that it will be an antinode. This is a fundamental. This is a first harmonic, still satisfying the conditions that this is an antinode and this is a node, and so on. Okay, how do we calculate the wavelength? This is like looking at American footballs. There's one and there's two. What you basically do is divide each wave that you see into quarter wavelengths as the smallest unit, and then it becomes very easy to count quarter wavelengths. There's 1/4, 2, 3. So we have 1, 2, 3, 4 quarters, which is one complete wavelength. How many quarter wavelengths are there here? 1, 2. So it's 2 quarter wavelengths, half a wavelength. How many quarter wavelengths are there here? 1, 2, 3. So we have 1, 2, 3, 4 quarter wavelengths, which is one complete wavelength. How many quarter wavelengths are there here? 1, 2, 3. So it's 3/4 of a wavelength. How many have we here? 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5, 6 quarter wavelengths. So it's 1.5 wavelengths. And we can see, going from here, 1 wavelength and a half. And so on. We have 3. Okay, you have to try to solve this problem. What is a wavelength, given that the waveform from here to here is 8.45 meters long? Pause the video and try to solve that one. Another question. This is 45 centimeters long. What is the wavelength? Pause and try to solve. Here again, the wavelength is 1.2 meters long. What is the wavelength? The waveform is 1.2 meters long. What is the wavelength? Pause and try to solve this one. Same again. Try to solve this one. Pause. Here again. Pause. For each of these, you can find the wavelength and you find the frequency. Given that the wave speed is 281.6 meters a second, you can find the f for each of these if you can look at the wavelength. This length is 32 centimeters long, so you should be able to find the wavelength and the frequency of all of these. And the same here. And the same here. This one is different. Okay, we can try this problem. Pause and try to find the answer. Try this one. Pause. Find the answer. Okay, now find the answer to this one. Pause. Figure the answer for this one. Pause. Figure the answer for this one. Pause. Figure the answer for this one. Pause. Do the answer for this one. Pause. The same here. Pause. Find the answer to this one. Pause. Find the answer to this one. Pause. Same here. Pause. Pause. pause, pause, pause,